You're here because you want to master transition metals with a University of Cambridge graduate. Let's begin. Many students often tell me that transition metals is just a topic where you memorize everything and regurgitate everything during the exam. Well, I'm here to tell you that that's not really the case. There are some parts where you need to memorize, but as a whole, transition metals, like all physical chemistry topics, require deep understanding of the topic so that you can apply it to any transition metal question that you see fit. Now, as per usual, before we start, I would recommend you go down to the link below so that you can download a free copy of the notes for yourself so that you can use it to go through this lecture and for your future revisions as well. D block elements are elements with their D subshell that is filled from D1 to D10, and transition metals in particular are D block elements that have partially filled D subshells, and these are usually found in the middle of the whole periodic table. Transition metals have physical properties that are very similar to giant metallic lattices, and you can refer to atomic structure and chemical bonding classes so that you can get all the trends that you need for melting points, atomic radii, ionization energy, and density. And because these were run through in the previous classes, I'm not going to dive into these today. On to chemical properties. Transition metals are known to have variable oxidation states, and they possess these variable oxidation states because this is due to small energy level differences between 3d and 4s orbitals, and there's a different number of 3d and 4s electrons that can be lost to form your stable ions, and these different stable ions are what's responsible for the different oxidation states. Your S block elements, however, are restricted to +1 and +2 oxidation states because any further removal of the inner shell electrons will require too much energy. You can predict oxidation states by using the number of 4s electrons and adding it up to the number of unpaired 3d electrons. Hydrolysis for transition metals is also very common to see. Now, some transition metal cations can undergo this hydrolysis, and this is mainly because they have a smaller cationic size and have a larger positive charge. This gives rise to a higher charge density and a higher polarizing power to draw electrons to itself from the O atom of the neighboring water molecules. If you recall, I've briefly run through this in my periodicity chapter as well. Now, this would polarize the OH bonds, weakening the bonds and making it easier to break to form the H plus ions, making these solutions slightly acidic. This is a diagram of Fe3 plus ion with H2O ligands and showing how the Fe3 plus is causing the hydrolysis of the OH bonds within the H2O ligands. Moving next to the relative stability of your oxidation states, in period 4, the stability of your +2 relative to +3 generally increases across the series. Now, you can look at this trend based off the E0 values. So for example, if you look at the E0 of M2 plus being reduced to M, you can look at the E0 and you can see that it's negative except for Cu2 plus. So this means that M2 plus is generally more stable relative to M. And this kind of makes sense because metals generally want to lose their electrons to form the ion. Since the E0 of the metals is more negative than the E0 of H plus to H2, you would expect that all metals, except Cu of course, to react with aqueous acids to give M2 plus. And also even further, M2 plus can further undergo oxidation to M3 plus. Generally, your E0 becomes less negative across the period as well. So the oxidation is becoming less and less likely from M to M2 plus across the period. Now, if you look at E0 of M3 plus, again, just look at the E0 value for certain trends. The E0 value for CO3 plus and Ni3 plus are positive. So this means the ions are more likely to be reduced. Versus for other E0 values for other transition metals, they are negative. So generally, the E0 becomes less negative across the period, which means that the oxidation of M to M3 plus is also less likely to happen across the period. And this also means that M3 plus is increasingly less stable relative to M across the whole period. Now, how about the E0 value of M3 plus to M2 plus? Well, if you look at both M2 plus and M3 plus, they decrease in stability across the series, as we've seen just now in my previous explanation. But if you look at this E0 value, you see that this E0 value increases across the period, meaning M3 plus is more likely to be reduced to M2 plus across the period. M3 plus will also decrease in stability more than M2 plus across the period, judging by this E0 trend. And this reason is actually similar to the third ionization energy across the period, where across the period, the nuclear charge would increase and shielding effect is relatively the same, and the effective nuclear charge would increase. So therefore, there's a higher EFOA between the nucleus and the outermost shell electrons. And because of that, it becomes increasingly difficult to remove the electron from M2 plus to form M3 plus. So you can see some parallels between ionization energy concepts from the first ever chapter to the transition metal topic that we have today. Of course, there are some exceptions. The drop in E naught from M3 plus M2 plus from Mn to Fe is attributed to the interelectronic repulsion in D6. And hint, this is actually a similar explanation to your ionization energy concepts in atomic structure as well. So here's a diagram over here. You see that because of this paired electron over here, it's actually facing some interelectronic repulsion. So it's actually easier to lose this electron compared to the electron in Mn. There's also another exception where the E naught value is actually more negative for Cr compared to V. Now this is because in D4, one electron is in a higher d orbital group, so it's more easily lost. And the observation is that Cr2 plus is therefore a stronger reducing agent than expected. So if you look at the diagram over here, you realize that this electron that I've circled is of a higher energy level and therefore is more easily lost compared to the electron in vanadium. And therefore, chromium tends to be a stronger reducing agent in the 2 plus oxidation state. So the overall takeaway is that you want to look at all the E naught values because you can use it to tell which is the more stable or the more easily oxidized or the more easily reduced species, or which species is the stronger or the weaker reducing / oxidizing agent. Moving next to the formation of complexes. So you must memorize this definition of complexes. Complexes are central metal atom or ion surrounded by other ions or molecules that are called ligands, and they are bonded to the central atom or ion via dative covalent bonds. Now this is possible for D block elements because they have a relatively small size and higher charge, so higher charge density and higher polarizing power, so it can therefore attract ligands. And this is also because transition metals tend to have low-lying d vacant orbitals, and they are able to accept lone pairs of electrons from other ligands and via this dative bonding. S block elements, however, are larger and have lower polarizing power, so they tend to be more involved in ion-dipole interactions compared to dative bonds. There are two important features of complexes. One is the net charge, and two is the coordination number. So coordination number is defined by the number of ligand groups, and these tend to generally be 4 or 6. Next, you need to know the definition of a ligand as well. A ligand is a neutral molecule or anion that contains at least one atom bearing a lone pair of electrons to be used in dative bonding with a metal ion or atom. So this definition is actually pretty easy to understand and memorize once you know the definition of a complex. All ligands are Lewis bases because they donate their lone pair of electrons, and there's also this concept about the denticity of a ligand, which is the number of dative bonds that can be formed per ligand, usually dictated by the number of lone pairs that it can donate to the transition metal. So if a ligand have a denticity of 2 or above 2, you can form these complexes that are called chelates, and these ligands are called chelating ligands. So an example of a bidentate ligand is this molecule over here, and you can realize that this NH2, the N, has a lone pair on each side, so you can donate 2 lone pairs to the transition metal as well. You also notice that the ligand is also long enough to occupy 2 spots on the transition metal. With 6 different spots on a transition metal to be filled, you will obviously also have shapes of complexes to be considered. Now this is very similar to the shapes of your molecules that is covered in chemical bonding. If there is a coordination number of 2 for the transition metal, the complex, it tends to be linear. So for example, this AgNH3 plus. If the coordination number is 4, it can be 2 shapes. It can either be tetrahedral or square planar. So tetrahedral is like CuCl4, and square planar is like cisplatin over here. Now which one is which? This tends to be learned from experience, and you just have to memorize some of the more basic and more common complexes that come out. For coordination number 6, it tends to be octahedral, and this is quite common for most complexes, 6 ligands, for example, FeH2O6, 3+. Moving on to one of my favorite concepts of transition metals is the color of transition metal ions and complexes. Now this is very fun because transition metals are colored, and they make for pretty fun experiments in the lab. And I hope that you have the chance to try them out yourself in the lab. We all know that transition metal ions have 5 d orbitals. There are low-lying vacant d orbitals some of the times. And these ligands that come will form a dative bond with the transition metal ion via the lone pair donation along the x and y and z axis. Now when the ligands approach along the axis, there will be some inter-electronic repulsion between the lone pair of electrons to form the donor atom of the ligand and the electron and the d orbital of the transition metal ions. And thus, the energies of your d electrons would increase. When ligands approach the x, y, and z axis, right, the electrons in the dx square minus y square or the dz square orbitals will experience greater repulsion than those in the 3 other orbitals. This is mainly because of how the orbitals align along the axis. And therefore, your 5d orbitals would just split into 2 different energy levels as shown in the diagram over here. This is the d orbital splitting. Now, the splitting of the d orbitals will explain the color and stability and the magnetic properties of the complexes. And this is covered in the d to d transition. So what is d to d transition? D to d transition is what determines the color of your complexes. In a complex, alright, the presence of your ligands will split the d orbitals as I said just now, and the d electron and the lower energy d orbitals will absorb a specific wavelength of light from the visible spectrum. And this would promote the lower energy electron from the lower energy d orbital to a high energy one, and this is why it's called the d to d transition. And the remaining wavelengths of light that is transmitted or not absorbed would give the complementary color that is observed. So you can see from the color wheel down over here, which determines the color. If the wavelength of light absorbed corresponds to red, for example, then the color observed would be green. You will always get the opposite color from the color wheel. Do take note that for d to d transition to occur, the d subshell must not be fully filled or fully empty. Otherwise, you can't have promotion of the electron from a lower energy d orbital to a higher energy d orbital. So just a concept for you to take note is that with regards to wavelengths of light, this delta E over here is actually inversely proportional to the wavelength of light, meaning that if there's a larger delta E, there's a shorter wavelength absorbed and therefore a longer wavelength transmitted, and vice versa. So what's an example of an answering technique for this whole concept? Some questions will ask you, why is CuH2O6 blue in color, or any other complex that's certain color? You have to start by explaining that the transition metal ion has incomplete d subshell. For this is the criteria for the d to d transition. And in your complex, the presence of your H2O ligands will split the 3d orbitals of the ion into 2 energy levels. And the 3d electron in the lower energy d orbital will absorb the light energy that corresponds to the wavelengths that is observed. So for example, it would absorb orange light to promote the lower energy d orbital electron to a high energy one, and the remaining wavelengths of light will be transmitted, which gives the complementary blue color. So you do have to memorize the color wheel in order to answer this question very specifically and according to the context. Some of the factors that affect your delta E are like the nature of your transition metal and its oxidation state. So generally your delta E will increase with oxidation state. This is because there's a higher charge density and there's an increased attraction of ligands, which leads to greater repulsion and therefore larger delta E. For the same oxidation state, the variation in delta E is quite irregular and there's no real trend for it. Next is also the shape of the complex. Now the shape will affect the number of ligands and the positions relative to the orientation of the d orbitals. And this results in different extents of your interactions between the lone pairs of electrons and therefore different extents of repulsion as well between the electrons. Now this will also lead to different magnitudes of delta E. For our own explanation's sake, we only need to know our explanation for the octahedral complex. And lastly, you also need to know that the nature of your ligands will affect the delta E. And this magnitude of your delta E would change as strength of your repulsion between the d electrons, point charges would change. And therefore, your delta E is actually a measure of the strength of your crystal field. You don't really need to know what crystal field means, but you just need to know that there are weak fields and strong field ligands. Weak field ligands give smaller delta E's and strong field ligands give larger delta E's. And weak field ligands are generally determined by the weaker metal ligand bonds, and strong field ones are just stronger metal ligand bonds. A common question that's asked is explaining why a solution of a complex is a certain color while the solution of another complex is a different color. And you just have to understand that this is because of the difference of the strength of your ligands. Now, you just have to compare that one ligand, for example H2O, is a weak field ligand and therefore results in smaller d orbital splitting and smaller delta E, giving rise to a certain wavelength being absorbed and therefore a certain wavelength being transmitted for light. Then if you look at the other complex, you pretty much say the same thing, where the other side has a stronger field ligand causing a larger d orbital splitting and larger delta E, that corresponds to a smaller wavelength of light absorbed with a larger wavelength of light being transmitted and therefore the corresponding color that's observed for the complex. Let's get on to ligand exchange reactions now. Ligand exchange reactions usually result in a change of color. Now this is determined and propelled by the strength of a ligand. The stronger ligands usually win weaker ligands in the complex ion. An example of that reaction is right over here. And you'll realize that the solution will turn from light blue to dark blue in this case when you switch up the ligands. And since the reaction is reversible, obviously you can reverse the whole reaction by, for example, neutralizing using dilute sulfuric acid, which will neutralize the ammonia ligands. And therefore, you shift the POE back to the left for this example over here to reform your copper with water ligands. Another factor that propels your ligand exchange reactions is the concentration of ligands. If you have a larger concentration of a different ligand, you can cause a ligand exchange reaction. So for example, if you use chlorine in higher concentration, you can turn your copper with water ligands to a copper with chlorine ligands. And this will cause a change in color from light blue to yellow. And this is observed when obviously you add concentrated HCl. You increase the concentration of your Cl- and you shift the POE to the right to form the copper with chlorine ligands. Now, of course, if you dilute the solution, you also dilute the concentration of your Cl-, and therefore you can shift the position of equilibrium back to the left with the copper with H2O ligands. There are also examples of compounds that are insoluble in water and they are actually made soluble through the conversion into a complex. So some examples are like chromium, that gives a PPT in the middle and then gives a dark green solution at the end upon excess addition of NaOH. And there are many other examples over here, some of which are quite familiar to you by now after doing your QA practice in the labs. For example, for zinc, you form a zinc complex over here, or you can also form a zinc complex with ammonia as well. You can also form a copper complex with ammonia that would dissolve the PPT that's formed in the middle. And some of the new ones that you might not have seen before are like for cobalt, that gives a blue PPT in the middle, and upon addition of excess NH3, you form a pale brown solution. Nickel, you start with green, and then you get a green PPT in the middle, and then when you add excess NH3, you get a dark blue solution. So I would advise that you memorize all of these solutions and the formulas and the colors of these complexes as well. Another classic case of a ligand exchange reaction is the exchange of CO/O2 in hemoglobin. Hemoglobin consists of 4 subunits, and each subunit we know is composed of a protein chain tightly associated with a non-protein prosthetic heme group. Now this heme group contains a Fe2+, which is the transition metal that we are talking about, and it exhibits a hexa coordination with 5 sites occupied by N. Now this last site is reversibly bonded with O2 and it allows hemoglobin to do a transport of oxygen. So for example, here it starts with S hemoglobin, but then when O2 is bound, you get oxyhemoglobin over here. Of course, this reaction is reversible, otherwise your O2 cannot come out of hemoglobin and to be given to the muscles in your body. However, when you have carbon monoxide, you can convert your oxyhemoglobin to carboxyhemoglobin. And actually carbon monoxide binds to hemoglobin at this same site about 210 times more tightly. And this is why carbon monoxide is so dangerous and can cause suffocation. This is because your CO is actually a stronger field ligand than O2. And there are also other ligands such as Cn- that strongly bind to this site, which is why people can also die from cyanide poisoning. Transition metals are also known for their catalytic activity. And they make effective heterogeneous catalysts because they have partially filled 3D orbitals that allows reactants to be adsorbed onto the surface. So your d electrons can be used to form bonds with reactant molecules. And the d orbitals are also energetically accessible and available orbitals, so they can be used to accommodate lone pairs of electrons from your reactant molecules to form bonds. So for this mechanism, you can actually refer to my reaction kinetics master class. And this is a little diagram that's also shown over here that shows the whole process of the adsorption and the whole heterogeneous catalyst mechanism. Transition metals also make good homogeneous catalysts. And they are effective homogeneous catalysts because they can exist in different oxidation states and undergo conversion from one oxidation state to another relatively easily. And for this mechanism, you can also again refer to the reaction kinetics master class. Lastly, as a little bonus, I've also added a whole table of all the colors of your transition metal complexes that you should know for the exams. Now, I highly recommend that you take this page and you just spend a few hours and memorize this whole page, because surely enough in the exams, they will test on the different colors of your transition metal complexes, and they will expect you to know the colors of different solutions and the color changes that are observed from, for example, a ligand exchange reaction. In summary, transition metals have a lot of fun concepts like determining the color of your transition metal complex, and with enough understanding, you should be able to tackle any transition metal problem and answer to the context of each of their questions specifically. If you're interested in enrolling in my chemistry class, you can click the link below so that you can book a free one-to-one consultation with me first, and I can go through any doubts and clarifications you may have and actually show you why my chemistry class would be a great fit for you. Also, if you like this type of content, be sure to hit the subscribe button below so that you can get more frequent updates from this channel. I'll see you in the next lesson.